How are y'all doing? So we're going to go into day 28. As you can tell, for the next 2 weeks, what you're going to be doing is you're going to do more than one reading assignment a day, and then you're doing the practice problems in the one pager. And what I'm going to do is I'm going to combine them together to give you either a low grade or a test grade on those. So that's what we're doing this week. So let's go ahead and jump right on in. So I'm going to see how far I get with section 11.1, and then we'll go from there. So the first thing that we're talking about here is we're talking about a simple harmonic motion. So when we're talking about a harmonic motion, it has to do with a spring and a weight. So the Hooke's law is the spring force, which is F elastic, equals the negative K times X, which is the spring constant, times the displacement. Now, the reason why it's a negative is because we're actually looking at the direction of the spring. So an example of a periodic motion, and what those examples are, is like a trapeze, a playground, a swing, a wrecking ball, a pendulum, a grandfather clock. Those actually have a periodic motion. So when we're talking about that, we have these three examples here. We have a maximum displacement where you have the spring with the block completely out or completely in. And then if it is at equilibrium, there's no force on the spring. It's just sitting in the box. It's not in the square, or the block is not moving. So it actually reaches its maximum. So in here, restoring force is a spring force always pushes or pulls the mass toward the original equilibrium position. Direction is proportional to the displacement of the mass. And then single harmonic motion is a motion, a vibration of a mass spring system. So in our textbook, we have an example problem. And in that example problem, it tells us a mass of 2.1 kilogram attaches to a vertical spring, stretches 6.2 centimeters from its original equilibrium position. What is the spring constant? So here's the diagram of it, and it's just showing you how the spring was without it, and once it got its mass, then it is negative 2.0 centimeters away from its original resting place. So for this one, we're going to take K, which is our constant, right? We're going to do a negative 22.1 times 9.81 divided by negative 0.062, and we should get 330 newtons per meter. So alpha y inner, because we have a fraction, we have a negative, open bracket, 2.1, close bracket, 9.81, down, negative 0.062 over inner, and I got 3.32 times 10 to the second power. That is the correct answer, but then also you can do the normal mode, which I did in normal mode, which is I got 330 newtons per meter. So then the next one for question number 1 is we start with, it says, suppose a spring sample, problem A, is replaced with the spring stretches 36 centimeters from equilibrium. So we're going to do 36 this time. We're going to have gravity again, and then we're going to have 2.1 kilogram. And so for that one, you're going to do your alpha y inner. You're going to do your negative, open bracket, 2.1, close bracket, 9.81, close bracket, and then we're going to go a negative 0.36, and we get 57 degrees newtons per meter for our answer. So then the next one tells us that we have a 3.0 kilogram, 9.81 meters per second squared, times 36 newtons per meter. So this one, we're going to do an alpha y inner, 3.0, open bracket, 9.81, and 36. And we should get 0.81. But if I went ahead and changed that, and I changed it to a negative 0.82 centimeters because I rounded it up. So then the number 3rd problem asks us a child exerts a 12 Newton force shooting a rubber band across the room. If the rubber band has a spring constant of 180 newtons per meter, what is the rubber band displacement? So we're going to take our alpha y inner, and we're going to do 12, and we're going to divide that by 180, and that's going to give us 0.0666, which we changed up to 0.67. Sorry, didn't know you couldn't see the calculator. And then number 4 says how much force is required to pull a string at 3.0 centimeters in equilibrium position if the spring constant is 2.7 times 10 to the 3rd. So this one here, we're going to do our negative 2.7 times 10 to carry 3 over close bracket, open bracket, and we're going to do a negative 0.030 close bracket, and we get 81, and that is our number. The next thing it talks about is the conservation of mechanical energy. What that is it was giving you an example of a bow, and what happens is elastic potential energy stored in the strength bow is converted into kinetic energy of an arrow. So as that energy is stored, we're pulling it back, and as the arrow is being shot, it's using that strength of that bow. It also talked about a simple pendulum, and it gave an example of trapeze artists where they have a fixed person, and that fixed string has what's called a bob on the ends of it. That's the weight and how it goes back and forth. And it also talked about restoring force. And on restoring force, it was talking about proportional to the displacement. So it's giving you here, the displacement is that angle there. And then also it was talking about changing in mechanical energy in a simple harmonic motion. So you have what's called potential energy here. You have your kinetic energy, which is here. Sorry, I'll get us something to follow that with. Yep, there we go. Okay, so if we're looking, this right here is your potential, this right here is your kinetic energy, and then your total mechanical energy is the line that's on top. Okay, and it talks about A is the maximum displacement, B is the equilibrium, and C is the total mechanical energy remaining in that system. And then also what they did is they gave you an example of simple harmonic motions. We have a maximum displacement. Here is the diagrams of the pendulum and the block, and it also tells you what direction the forces are going with vectors. And that is the end of that section. So what I'm going to do is I'm going to stop the video now, and then I'm going to post this one, and then I will do the second section. Make sure you do a one-pager for this, and also, please make sure that you have done the math that I've shown you on this video.